Today's webinar, like all webinars, is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, please use the chat window to type in your questions or to communicate with others. During the Q&A section at the end of the talk, please either indicate in the chat window that you have a question or turn on your microphone and your video so we know you have a question. Today, we are fortunate to have with us the team of Leon Krischer, Simon Staehler, and Martin van Driel from ETH Zurich. I pulled this from Leon's webpage, but I think it rings true for this entire team of researcher developers in that they work at the crossroads where seismology meets computational science, big data engineering, and machine learning, developing and maintaining production-grade scientific software, and making them available as open-source packages to a worldwide user base that many of us benefit from. So today's speakers will introduce us to the new developments in two of these, that is AxiSEM and Instaseis. So the screen is all yours.
Okay, thank you, Lorraine. So just to repeat, this is a talk that we're going to share between the three of us. Everyone should take like about 20 minutes, or maybe we think we might be a bit quicker, so to have questions in the end. I also want to acknowledge the fact that most of the work was done in collaboration with Tarje and Nissen-Meyer from Oxford, partly during my PhD and the other guy's PhD. And it's probably not the most recent research we have done, but it probably has turned out to be one of the more useful things we have done so far. And so today, I really want to talk about how we can use AxiSEM, Instaseis, and a newly developed web interface to that from Iris to compute seismograms really quickly. So the idea is that we use a spectral element method that's tailored to the global domain. I'll talk a bit about why it's really fast in a moment. We'll release that code open source on CIG in 2013. And it's really used around the world, and we are collecting citations on the corresponding papers right now. So here's the download number from 2015. I didn't update it because it's exactly the same for the last year, but much more concentrated in the US, actually. And importantly, in contrast to some other codes that are tailored for the global seismic wave propagation, we feature full-on isotropy. We have attenuation. The code scales well on supercomputers, and we actually have a benchmark to another code at the highest frequency that we typically observe in global seismology, that is 1 Hertz. The downside in comparison to some of the normal mode codes is that we do not include gravity, and we also do not include rotation. And so to get back to why we are able to go to these high frequencies in contrast to other full three methods, it goes back to an idea that Tarje pushed during his PhD, and it's that the model is axisymmetric with respect to an axis that goes through the center of the planet and the source. And if you do that, you can then develop the azimuthal component, or the azimuthal dependence of the wave field in terms of a Fourier series that stops at degree 2. And that's why we effectively then only have to solve a 2D problem in this kind of D-shaped domain. And for that, we use the spectral element method. The azimuthal component is, as I said, analytically. And that's how we essentially get fully 3D waves by using a 2D numerical method. And that allows us to go to these high frequencies. On the right, this is just the way we represent the wave field inside each of the elements. These are the spectral element basis functions. And so can I go back up? Yeah. So the nice thing is that the wave field is represented by these very smooth functions, and so it's easy to compute derivatives with very high accuracy. And we will get back to that when we talk about Instaseis in a moment. This is again about the performance. So what we are comparing here is the number of CPU hours you would need to compute 1 hour of seismogram on a full global scale in AxiSEM and SpecFEM. What you can see is that the scaling in SpecFEM, as you would expect for a fully time and space discretized method, goes with the power of 4. So you have 3 space dimension and 1 time dimension. If you refine your mesh, you also have to decrease the time step. And in AxiSEM, you get away with the power of 3, which is the 2 space dimensions of the numerical domain and the time. And when you look at how this depends then on frequency, that really tells you why it's possible to do like these high frequency ranges that are interesting, especially for body waves with AxiSEM, but it's going to be really expensive when you want to go there with SpecFEM. Another advantage of this decomposition of the azimuthal dependence and the source receiver plane dependence is that this allows us to store wave fields. So while in 3D, storage would just not be sufficient for storing the full wave fields, we can actually afford that. And what you see here is, again, as a function of the shortest period, it's the database size. So if you store a full waveform database for different situations, down to different depth, different components, and different duration. And what you end up with, so it turns out that in many cases we use 2 seconds, because that's what was really useful. You get away with a standard hard drive that you can just buy off the shelf. And this was basically a talk that I gave 3 years ago, but I added a couple of slides with the newest features. One of the cool things I think about AxiSEM is it has been really stable for the last couple of years, and we really basically kept the interface the same, and we're only bug fixing and adding very small features. But these ones are, I think, very useful. So what we added, I guess, in the course of the last half year is we can now do local domains. We also have the absorbing boundaries at the edge of these domains. We also have oceans, so here you have a water layer on top with appropriate boundary condition on top, and we can also have explosions in the fluid. And just to show you how cool that is, I prepared a little movie. So here you can see the absorbing boundaries in action. You can see the boundary condition between the solid and the fluid, so you get these Schalter type waves, and you also see the reverberations that you get in the water layer. Anyway, so this is just on the few new features that we have. I'm trying to close this right now. On the AxiSEM side. So AxiSEM, as I said, is a forward tool. So basically you can put in a source and produce that wave field. What is important is that we're coupling this to a software that we call Instaseis. And Instaseis takes these wave fields that are generated with AxiSEM and allows to then extract seismograms from these wave fields. And it does it in a way that is accurate, to the same accuracy that the spectral element method allows in terms of the spatial and temporal interpolation. And we offer a nice Python interface with the client-server infrastructure, so that if you get the databases in some way, you don't need a supercomputer yourself to then use these wavefield databases. And this becomes particularly interesting if we consider reciprocity of the Green's function. So this is an exact mathematical property that the Green's functions have. If you exchange the source and the receiver location, so here you have the Green's function as a function of the source and receiver location in time, multiplied by the moment tensor. And if you exchange the source and receiver position, you still get the same seismogram. You actually also have to transpose the moment tensor. So this is an error in my slides here. It should be QP. And so because receivers in spherically symmetric, because receivers on Earth are usually on the Earth's surface, you can then use that to essentially just simulate two AxiSEM runs. So you have the vertical and the horizontal, which is invariant under rotation about the vertical axis. And instead of doing a forward simulation from the source to the receiver, you do these 2 runs and just store the wave field throughout the volume where you might expect sources. So on the Earth, that's probably down to a couple 100 kilometers. And this way you can build these kind of Green's function databases with exactly 2 runs in AxiSEM. So on top of the fact that AxiSEM is a lot faster than 3D, you also gain the fact that you need to do a lot less runs here. And when we say fast, we really mean essentially instantaneous. And that's also where the name Instaseis comes from. And to highlight that, we have a short movie here. So we have this graphical interface where you can just click into a map to select source and receiver location and immediately see the update of the seismograms on the left-hand side. You can also change, or you can hover your mouse over these faces. So these are great theoretical rivals to help you understand what you're looking at. And you can use these sliders to just change the moment tensor. And I guess finally, the last slide I want to show is the depth slider. Here where you can just go through different depths. So now we are making the event shallower and shallower, and we can see that the surface waves change by a lot. Essentially go from overtones to the fundamental mode. And the body waves are very much insensitive to that depth. So some of the highlights, we by now we actually do have an interface to SeisCom3. So for those people who use an observatory and use SeisCom for the data handling, you can immediately use Instaseis to produce synthetics for source inversion. We have extensive tutorials on Seismolife. Leon is going to talk about that in a moment. And in the last year, maybe you took notice of that, the InSight mission that's going to place a seismometer on Mars by the end of the year had this blind test challenge, and we actually computed the data, the synthetic data for the test using this setup. So that's a nice success of the software. So finally, I want to get to Syngen. Syngen is essentially a web interface that's hosted by Iris. So they offer various ways of accessing synthetic seismograms on this web page. You can either go through direct HTTP, you can use your browser with a post. They have their own software, which is called FetchSyn. What I usually use is either a standard data source in OpSpy or directly Instaseis. So in fact, you can actually run this this GUI that I just showed directly from Syngen right now. And the power of this becomes really visible when you look at all these models that are pre-computed and available. So this totals to something about, correct me if I'm wrong, Simon, maybe like 15 gigabyte of data, terabyte of data, sorry.
Yes.
And instead of downloading them to your local disk, you can just query individual seismograms directly from Syngen without big downloads or big local storage.
15 terabytes and 100,000 CPU hours, which is stored there.
Okay. And so, yeah, we do think that this comes, for example, is very powerful for things like education, where people don't have access to supercomputers or extreme storage. So to conclude, I said that already, but when I was making this this slide on future directions, I realized we haven't really changed a lot in the last years, and there's not so many things we plan. The software is apparently in a rather mature state, and this is just used. And some of the things that we're planning to do is including different solvers other than AxiSEM. in establishing Instaseis as a more general interface to using output of numerical solvers such as AxiSEM 3D solvers or some normal mode codes. For Instaseis, we also plan to directly use this cardec type input files, so you could directly use Instaseis with cardec. And what we haven't done yet is to establish these local scale databases on Syngen, so that these are also available without download. And with that, I want to hand over. Lorraine, do we have a short question section right now, or do we want to go on to more practical stuff immediately?
Well, if anybody has any questions right now, I would say go ahead and type them in, or else they can save them for later. I haven't seen anything in the chat box, so.
Okay. In that case, I'll hand over the mic to you.
Okay, so the next part will be, if I get it on the screen. Okay. The next part will be about calculating Instaseis waveforms yourself at home. Leon is there. Here. Okay, so fundamentally, if you want to run AxiSEM, it's pretty straightforward, I would say. Basically, as a prerequisite, you have to download the code, obviously. For that, we would recommend to use the current version, the current master branch on GitHub, and not use the last release, which doesn't, for example, doesn't contain yet the local runs. We plan to release version 1.4 in the next days, but yeah, give us a few days to do that. So after downloading the code, you basically, we have some templates, a template make file, included template input files, so you copy them. And afterwards, check whether your local compiler options match those predefined ones, compile the code, and then run it. I saw, was there a question in the chat? There was something lighting up a few seconds ago. Did you see that? Yes. Okay. So then, if that's not the case, I'll do just that and show and present you. Yeah. Okay, so Leon is checking whether there's a question in the chat. Okay, we didn't find one. Yeah, I'll make that a bit bigger. Okay, so we obviously start with downloading AxiSEM. github.com/geodynamics/AxiSEM, and try not to do any typos. So this is less for you to join, but more for you to see it once. Okay, that is it. Okay, now I think there's here, what does it say more? Oh, there are some questions in the chat. Okay, so the questions where one person is Kyle Smith is saying he doesn't hear any sound. Okay, now he can. The presentations, he asked whether the presentations will be available online. Yes, they will be afterwards. And the presentation slides as well, Martin?
Afterwards, I mean, the whole movie is going to be recorded online. Okay,
the whole movie, the whole presentation will be online. What are the system requirements? That's a good question. So that depends highly on the frequency you want to simulate. If you want to, just showing you how to do a simulation at 50-second dominant period, which in SpecFam lingo translates to 25 seconds. Globally, if you want to do a 1 second, 1 hertz simulation, you need to go to an HPC system, and you land somewhere at 10,000 CPU hours roughly. I hope that answers your question. Okay, now how can I close that chat window? Thanks. Check. Okay, chat is on the other. So we go to the AxiSEM directory. As I said, we do copy the templates, which are the template make file and input file. There's this one file, this make axisem.macros, which contains all your compiler flags. This is usually, if you're on a Linux machine, this is not a problem. It tends to become, or some people have reported problems when compiling it on Mac, because there you need to take care of the compiler paths and netcdf paths. Why is this taking so long? Okay, no. So for example, in case your MPI run command is not the same, which may be the case on a supercomputing system, and you can change that here. You can set the path to the netcdf libraries, and you can also set the compiler flags. So in this case, we're using GCC with regular optimization flags. Okay, now that we've checked that, we can compile the code in parallel, which should go pretty fast. And while it compiles, I'll go to the second slide. So the old, in case you've used AxiSEM before, you will still know the old mode, where you basically go to the measure, create a mesh in the measure directory with this submit.csh. You move the mesh to the solver directory. You go to the solver, run the code, run the solver, which is the actual AxiSEM code. And afterwards, do so-called field transform. So transform the written wave fields into a way that Instaseis can read. For those people who are mainly interested in creating Instaseis databases, we have streamlined that and basically combined everything in one Python script, which can be run immediately. In a moment, it supports local runs, and it supports runs on our supercomputing system, CSCS in Switzerland, which is a Slurm-based queuing system. We could adapt that to other HPC environments if people request that. Okay, so in the meantime, the code has compiled, and then I can show you that submit script. 2H, what a pity. Okay, we are running that on another machine, and apparently we're having a very slow screen connection. I'm sorry for that. So this submit script takes one job name that you can just choose yourself, one mesh name, which can either be an external mesh file or one of the meshes that are included with AxiSEM. And then you need to tell it a mesh period, obviously, and everything else is basically is not mandatory. I would do less typos, then it would work easier with that. Submit.py. So we'll do a test run with just prem. We call that prem test. We use the internal anisotropic prem model. Prem any, and we do this run at, no, it's not AI, prem. Yeah, this is our internal gigabit network is surprisingly slow at this. Prem NAN. So this is not AxiSEM, which is slow. It's the connection to the other computer. Ja, ich weiß nicht, ich würde es jetzt ungern verändern. Why is it so extremely slow right now? So I do that at 60 seconds. Okay, now I forgot one thing. Okay, shit. So, and I tell the tell the mesher to decompose the mesh into 8 domains. Since we're having a 12 core machine, we can decompose it into 8 domains. 12 actually, unfortunately, wouldn't work because of the way AxiSEM decomposes meshes, but 8 would work. Bin ich schon bei am Anfang von n Theta? Okay. So, okay. Ah, okay. Okay, so the code has created a mesh which goes extremely fast for a 60-second mesh. It decomposes that into for 8 cores, and then it does the 2 AxiSEM simulations which are needed. So one, the horizontal force source solution, and afterwards it will do the second run for the vertical force source, which then by reciprocity create the vertical component seismogram and the horizontal component seismogram. We can check the progress of these runs. Here you see this horizontal run is already at 85–90%. The vertical run afterwards will be considerably faster since it's the source is only a monopole source then and not a dipole source anymore, and of course doesn't excite any motion in phi direction. So after the second simulation is done, the script converts the output files into a Instaseis database. So shall I now dare to start the Instaseis GUI? Over the it has become slightly faster now. Great. I open this database, and just as Leon or Martin showed previously in his presentation, now we're having the database, and with on the GUI we can extremely quickly calculate waveforms for different source receiver locations. To show you one quick example how you can change or how you can calculate the database for another model. As Martin said before, it's not necessary to calculate a prem database anymore since they are all on Syngin already. AxiSEM writes out the model it has been using into a text file, even if it was an internal model already. Are we already at DIX? Yeah, 1D model. What I want to do is creating a prem model without a crust and compare the two results. If I'm looking directly out of into another screen, this is because we're having a second screen where this delay does not happen, and so I can work there. So this is what you see here is a typical input file for AxiSEM. It's a model input file for AxiSEM. It contains in each column, for example, first the radius, then the density, the p velocity, the s velocity. And those can be anisotropic. You can actually remove the anisotropic terms and the attenuation and the Qs in the last row, and then have a purely isotropic or non-attenuative simulation. So what I want to do is basically remove this first block, which is the crust. Remove these two first layers from the model. And then I can do the same AxiSEM simulation for this model of Prem without a crust. Oh, there's a okay, there was a rather specific question from Paris, Alemany, Hector, Alejandro. I will answer it in 1 second. I will kick off the simulation for the Prem model without a crust, and then while that runs, answer his question. This Prem no crust. So we're doing now a simulation of Prem without a crust at the same 60-second period, and also with 8 cores. It will be slightly faster than the previous one because it needs less small elements for the crust. So the question was of Perez, Alemany, Hector, Alejandro. He wanted to calculate a Green's function database for a mass model using AxiSEM and got an interpolation error. That interpolation error sometimes appears as the usual thing. What happens, and you might check whether you got that right, is that you have 2 layers which are overlapping in your input file. Otherwise, if that is not the case, send us a mail with your exact input files and we'll have a look into that. But the typical case is that you're accidentally having overlapping layers in the input file, also the velocity model input file. Okay, so in the meantime, the other calculation ended. So we can now compare the output of the 2 databases. One is the Prem simulation we did in the beginning. And the other one is the Prem simulation we did without a crust. And I will just very quickly, or just quickly plotting a seismogram or seismograms for a source in 45-degree distance, and you immediately see that body waves are more or less the same, whether you have a crust or whether you don't. For the P wave, there's no difference. For the S wave, there's a little difference. But of course, the Rayleigh wave train is very different. I mean, for the green curve, which is this one, without a crust, the Rayleigh wave obviously arrives a lot earlier because it's these mental velocities, while for the Prem model with a crust, it arrives a bit later since it's these lower velocities of the crust. And that happens even at 60-second period, which again in SpecFEM definition is roughly 30-second period. So that is would solve your usual use case that you want to calculate a Instaseis database for another velocity model. And again, this is in the moment based on the current GitHub version of the code, GitHub master branch, and it will, so download that if you want to use this version. Otherwise, wait a few days or weeks, hopefully more days than weeks, for the release of AxiSEM version 1.4, which will be advertised over the CIG mailing list and also the IRIS mailing list. Any more questions on that part? Yes, we do have other models such as ISP. That was a question. I'm personally focusing on body waves mainly, so I'm not really using Prem most of the time. What we do have are several varieties of Prem that Tarje implemented a long time ago. So an isotropic Prem, an anisotropic Prem, a Prem without a crust, Prem with a solid core. But more importantly, we do have AK135, which is the original AK135 by Brian Kennett. AK135F, which is the combination of AK135 with normal modes by Kennett and Montagnier. and ISP91, which is obviously ISP91. What we can, maybe another thing that I should, maybe another thing that I could show very quickly now is that with this script you can also do AxiSEM runs for the local version by defining these maximum colat parameters, which with you can set the maximum colatitude of the mesh. So 180-degree mesh is the whole sphere basically, because it's analytical solution to get the other 180 degrees. 90-degree mesh is then only maximum distance of 90 degrees. And of course, if you set that to something like 1 degree, so 100 kilometers, you can increase the frequency or the minimum period of your simulation a lot. Similarly, you can set the maximum depth of your model to something like 100 kilometers if you're only interested in local simulations, and then do simulations of at 1 hertz on a local laptop with a few cores, basically. So I think I would end it here. Are there any more questions? Good. Then I'll pass over to Leon, who will talk about the SynGen database and how this can be accessed from a local machine. Thanks.
Hello, everyone. Yes, I'll show the SynGen, but I'll also show how to just actually use Instaseis from within its Python interface. So what I'll be using are so-called Jupyter notebooks. And if you've never seen these, well, I guess have a look. But basically, I'm in a certain folder with, where there's a collection of Jupyter notebooks. And I'm just going to launch the Jupyter notebook server. Jupyter notebook. And this will open a browser and show me all kinds of notebooks. And we prepared one with the new one for the regional and local scale Instaseis. And you will find this starting, oops, that's the wrong one actually. You will find this starting from tomorrow. You will find this on a website of ours, which we call Seismolive. So if you've never seen these notebooks, what they are, they're basically an interactive computing environment where you can freely mix graphics, formulas, text, together with executable code, which really helps you to either explain things or to just explore parts of your science or your workflow. I'll hide a couple of toolbars so you have a bit more space to view things. Also make this a bit bigger. Okay, as I mentioned before, these things will be on Seismolive. I'll show this a bit after this short presentation. You can access it here. This is a notebook from us. So in Instaseis, we've actually not shown this yet, but there's a website. If you go to instaseis.net, there is the Instaseis website where you have all kinds of documentation, a few videos. You have the documentation for each of the functions. You also have a short tutorial of all the things we have, how to install it, and many other things. Another thing to mention, what I'll show now with the local scale Instaseis, that is also not yet released. So this will be in the next Instaseis version, which we hope to release end of this week. Okay, what this notebook contains, basically a short introduction to the basics of Instaseis and how you can apply this to a regional scale database. And this is a picture of the mesh we're using. So it's the same one Martin showed the video before. It's a 50-kilometer mesh in the horizontal direction down to 10 kilometers. And there's an ocean layer on top that has the ocean floor is at 2-kilometer depth. So that's just a picture of it. There's also a video here that shows the kind of a similar simulation in action. And you can see the same effects Martin showed before. And once again, the advantage of these regional scale databases is that you can really push this to very high frequencies. So it's very easy to go to 10, 20, 30, 40 hertz if you make your domain small enough, which for some applications is what you'd like to do. So we go to the tutorial. So Instaseis is written in Python, so also to use it, you have to use Python or the web interface, but we will use Python here. And if you've never seen Python, I guess you can just try to follow along, but it's not that complicated. The first thing you always have to do in Python is to import things you want to use. And what this first kind of code cell shows us, so this line here makes all the plots appear in the notebook. That's what we want. We want to show them in the browser, not somewhere else. And this is just the plotting interface for Python. What we also need is Instaseis to be able to actually use it. And the way these notebooks are set up, so you always have code cells, which you can then execute. And then once these executed, they will show a number here. That means they are, now they've run, and the results, it's available. So the first step with Instaseis is always to open a database. Therefore, we have an OpenDB function, which is also documented on our website. That shows how to use it, all the things it can do. What this function does, it detects the type of database. So currently, all of our databases are still calculated with AxiSEM, but we have a couple of different formats that have been grown historically, and this can also connect to what we call remote database and also to the Synchron service. So kind of depending on what you pass here, it will either open a web connection or open a local connection to the netcdf files, and then you can start using it. So to actually do this, you just say like database equals Instaseis. You can type Instaseis.opendb, and I'm going to use a local one. What do I call this? Local ocean. That's just a folder that contains the database. You can just do it. It opens pretty fast. You can ignore this warning here. That's from a dependent package. Now you have, in this DB, you have the database object. You can print this and view a bit of basic information about the database. So if you just print this, it prints some information. So you see here, okay, that's kind of the type of database. That's a reciprocal Instaseis database. We also have like forward database and some others of a certain version, and it has been generated with these parameters. First thing is pretty important is component. So you can see here this has vertical and horizontal components. You can also make databases with only one or the other. Yeah, some water, thank you. Then the chosen velocity model, you see some attenuation. You can see the dominant period here. So this is fairly high frequency, but it's also a small database, and a couple of other things. A couple more important things are the seismogram length, so the duration of the database. Again, this varies depending on what you actually simulate. And here you see the min-max radius and the min-max distance. So this is basically the spatial extent of where you can put the sources. So you see you can put the sources in the first 10 kilometers of the planet, and at a maximum distance of 0.5 degrees, or approximately 55 kilometers. And you can hear this size, it's about 0.5 gigabyte, still fairly small, but these tend to get larger once you increase the frequency or the size. Okay, now to actually calculate or extract seismograms, what Instaseis requires is knowledge about the source and the receiver. For this example, we'll manually specify both, but what you can also do, you can read any station or event file format that OpSpy can read, which excludes most nowadays common file formats. To actually see this, have a look at some of the other examples. So the receivers, you specify these with coordinates. And so just going to call here receiver is Instaseis, and then there's Instaseis, there's the receiver class. And this takes a number of parameters. It takes the coordinates, so latitude. We're just going to put this straight at latitude, longitude 0. Receivers for the reciprocal case cannot take a depth, because the depth is determined by your database. In this case, the receivers will always be placed at the seafloor. And you can also optionally specify like network and station codes if you want, which are the seed identifiers, which might make it easier to work with them later on. Okay, so that just specifies the source we have. If you want, you can print it, and we'll show some things. But basically what we do, that's a receiver object. These are fairly simple. The next thing we have to do is we also have to initialize or create a source object. These are a bit more complicated. The most common or simple one is also to specify the coordinates, again, latitude, longitude, and depth, and the moment tensor components. And the ones you do not specify, the tensor components you don't specify, they will be set to 0. What we do here is we specify an explosive source at an epicenter distance of 10 kilometers at a depth of 3 kilometers. So we just say source, with Instaseis source. And again, we have to pass the coordinates, again, latitude, longitude. We make our life very easy and just place the source and 0 both on the equator at a certain distance. So we set the latitude to 0 and the longitude to 0.1, which is 11 kilometers about. And then you can specify the depth. In this case, it's a meter. And we set 3 kilometers, so that's 3,000. And for an explosive source, we need to set all, for an isotropic explosive source, we need to set all diagonal components of the moment tensor to the same value. So we just say MRR, set this to like, I don't know, doesn't really matter here. It's just a scaling issue. So we set it to the same value. These are in Newton meters. Again, you can pass any kind of tangential components you want. There are also various different ways to initialize these, for example, from strap to break or various file formats. And you can again print this. Let's see what comes out of it. I have a source object with a default origin time. You can set this also here in the constructor if you want, and also calculates the magnitude based on what you passed here. Okay. What you now, once you have a source and the receiver, you would take those two and put them in the get seismograms method of the database you initialized previously. So you can also see here that's the documentation on our website for the get seismograms method that documents all the various parameters this takes, but you can have a look at this at your own leisure. So to get something, you just call say an object name, we call it st, and then database.get seismograms. These take a source, which pass here, and the receiver. And that's all they take. Then the library figures out the rest, what to do. What comes back here is an ops_by_stream object, which is also documented here. So ops_by is the Python library to deal with all kinds of seismological I/O and processing needs. What this means for Instaseis is that it's very easy to just calculate something that it can actually do some work with it. Which also means you get all the functionality of the stream object. So you can get it, you can print it, and you can also plot it. We see here is you print it. Okay, now we have 3 components, set vertical north and east, certain times, at a certain sampling rates, and a certain number of samples. And here are just some plots of it. So vertical component, we have nothing on the north component due to the explosive source and source receiver geometry, and we have something on the east component. I'm not going to go into many details here. 2 important arguments for the get seismogram function are components and the DT. So the first one is basically just says which components you want to retrieve. Must be one of vertical northeast or radial and transverse. This is important because the less you choose, the cheaper it is. And the second one determines the sampling rate. And if you need a specific sampling rate, just specify it right here, or the sample spacing, because internally upsampling is done in a very high quality sync-based reconstruction filter, so it's fairly accurate. Just to demonstrate this quickly, we also, again, just going to copy this from up here. But we will specify the components. So we know, let's say we want the vertical and the radial component, and we want the DT of, I don't know, 100 hertz about. You can see we extract this, we print it, and we plot it. Now we get 2 traces at 100 hertz. You can specify even any fractional number here, and this we get the seismograms. They look exactly the same as here, just upsampled. Yes, what we do not do, you can only upsample with this. If you try to use this for downsampling, so a sampling rate less than what the database has will raise an error because we don't want to deal with any kind of aliasing filter issues. Now there's a small kind of exercise. So what's the effect of basically if the source is either in the acoustic medium of the ocean or in the solid medium of the crust. So we're just gonna plot some seismograms with sources a few hundred kilometers above and below the ocean floor and try to study the effects. So this is just a modular thing, so we actually get a bigger figure to see something. And now we loop over a number of depth. Oops. For depth in. So the ocean bottom is the depth of 2 kilometers. So we're gonna go from a depth of 1.6 kilometers in steps of 200 meters deeper. So 2 kilometers, 2,200 kilometers, 2.2 kilometers, and 2.4. And we just generate different sources. So insta source. And we're going to use the same parameters as before. So we're going to put them at 0 and 1 latitude, or open one that's again about 11 kilometers away from the receiver. We're going to choose the same moment tensor component as before. Let's put a break here. 27. GT 27. And we're gonna just the depth in meters because we're in a loop right now. We're just gonna put this to the depth, the loop variable. That's the loop variable here. This will be set to each of those. And then we'll just calculate this. Debate get seismograms, source, receiver. And we only know, let's just limit it to one component to make it easier. This gives us the stream option. We're just going to plot the data of all of those one by one. So we're just going to call it PLT.plot, which is the monolith plotting kind of interactive mode. We're going to plot from the first component of the stream. We're going to plot the data, and we're also going to label it, so we can later see which depth of what. We do this for each loop, and at the end we'll show a legend, so we actually can figure out which wiggle corresponds to what depth. And this doesn't work. Get components. It's an S here. And what you see here that these are all wiggles for with seismogram for sources at different depth. So the color here that corresponds to the source depth, and what you basically see here that the seismograms, without going into any further interpretation, they do look pretty different depending on if the source is in the ocean or if it's in the solid medium. So this was just a very quick introduction of how you can actually use Instaseis. We'll now show very quickly also how to use the Syngen web service within UpSpy. To do this, we actually we try to use the Seismo Live website live. Please don't, let's not try this all at once, okay? Otherwise it might crash. So we go to Seismo Live, open a notebook, and have a look at the Syngen tutorial here. So Syngen, again, if you've never seen this, it's an Iris. It's a service hosted by Iris. These are, as Martin mentioned before, these are databases, Instaseis databases that are hosted by Iris, which you can just access with a normal web client. So you don't have to calculate or pre-compute anything. And they offer various Earth models at various frequencies with different components and things. And you can just, if you only need, let's say, a couple of hundred or a couple of thousand synthetic seismograms, it's a very good service. It's basically zero prerequisites. Okay, what I'm going to show in this notebook is how to use this from with an UpSpy. So you don't necessarily need to install Instaseis. You can use Syngen with Instaseis, but you can also just directly use it with UpSpy or with any kind of HTTP-enabled client, basically. So this is just kind of a short some basic setup. What we'll do here is for a real event, we're going to download the real event data, which I'll not show into any details. And then I'm going to compare the real data to some synthetics calculated with Instaseis. And what this block basically shows, it initializes an UpSpy client to actually download real data from the Iris DMC. So we're just going to initialize this here. We can optionally choose to acquire some event information. And so we just get information about one event, a very specific time, a certain magnitude. And this yields us one event, which we'll just simulate. We'll also download the actual waveforms from a certain station. I'm sorry if this is a bit quick, but you can try this out at your own leisure. Basically, all we do now is download event, station, and waveform data for a real event to later be able to compare it to data. We'll now take this data we downloaded, remove the response, and deconvolve it to actual ground motion, to displacement. So now we actually have data in terms of meters. Now, last thing we need is stations, and we're going to plot that. And what we now do in this thing, that's what I actually want to show, is how to download data with Syngen. So what UpSpy has, it has what we call it a Syngen client. You can go on UpSpy client Syngen and import the client, and you can initialize it. And what this example shows is how you loop over a number of different Earth models and get seismograms for this. So what we do here, that CS is the initialized Syngen client, and we call the get waveforms methods of this. The model name is one of the parameters. So this has to correspond to one of the models on the Syngen website for a certain network and station. So what the Iris implementation does, if it knows the the station, it can look up the coordinates. And the same is with a certain event catalog. So for the GCMT catalog example, you can pass the ID, and it will figure out the location and the moment tensor component for this particular event, which corresponds to the one we've did previously. You can also resample server side. So this resamples at 20 hertz, yes. And no, 20 seconds, I'm sorry. And also the units, you can have either displacement, velocity, or acceleration. And we also only again care about the vertical components. We'll now do this in a loop. And assuming that too many of you follow along. This should be pretty quick. And the rest is just some kind of, oh, here we go. Some kind of scaffolding to get it done. So here we have seismograms for various different models for the same source. And well, the notebook space is, well, it does a couple more things. It calculates the theoretical arrival time for the first arriving P phase using a tau P implementation. And last but not least, we also just gonna plot it here. And what you will see here is this is the actual recorded filtered data, and all of these are Instaseis synthetics computed through various Earth models. And you see that at least for the body waves, the fit is actually rather good. So this is a valuable tool also for like data quality or other things you might want to do. With this, we would have a lot more things to show, but our time is basically over. So if there are any questions, we would be very happy to answer them. Otherwise, thanks for listening. In the chat, there are 2 more sources for online databases, but I think Martin or Simon can say more to this.
So these are databases. Since the question of Mars databases already came up, these are databases that were created for Mars in preparation of the InSight mission. This is the first link, and the second link are databases created for several ocean worlds of Jupiter moons and Saturn moons, where you have an ocean below an icy surface. And in the moment, there's little use for either because there's no seismometer on Mars or any of the other places. But at least if you want to look at the spectrum, how waveforms or how seismograms can look like in other planetary models, this might be interesting. Or if you're working on the InSight project at another place, you can also use those for preparation. Good.
Great. Well, thank you so much for giving us quite the tour de force between AxiSEM, Instaseis, and Syngen. That was a lot of work, and it was a lot of bravado there going to trying to do the typing and talking and live demo all at once. So thank you very much for giving that webinar. I think I probably speak for everybody here that we appreciate your efforts for supporting the community and the large commitment that you make in making the software available and usable to the community. And, you know, as being researchers, you know, it is important that we all get credit for the work we do. So I was wondering if you could tell everybody here how to properly cite the software if they're using the software in their research.
So there are 3 papers in total on the, as one on AxiSEM, which is from 2014, Nissen-Meyer et al. I think they are linked on the Syngen page. Do you still have that open somewhere in the background?
Oh yeah, here. Yeah, like the Instaseis links the Instaseis and the...
So the first paper was the AxiSEM paper, if you really calculate something with AxiSEM. The second one is the Instaseis paper, which is van Driel et al. Of 2015, which Leon is just highlighting on the Instaseis webpage. And the third one is by Leon et al., Leon Krischer et al., a paper on Syngen from SRL last year. So depending on which services you use, cite either of the 3 or best all 3. Yeah, and on the InSight, on the Syngen homepage, there's actually a link to all 3 papers.
Great. So there's, you know, a lot of talk about reproducibility in research. So I was wondering, do you provide a mechanism to actually cite the software itself as a research object versus the paper on the software?
I'm actually not sure for Instaseis. For OpSpy, we do have DOIs for the individual releases. But personally, as researchers, it would help us more if you would cite the paper. That's just a fact of life.
Yeah, it is. Yes, but I think also the editors are asking more for people to cite the software as well as provide data to back up your research papers. So I don't know if you have any thoughts on that as well, if you've come up across this when you're publishing your papers about the new data and software requirements that editors are now requiring.
What we actually do as part of a Seismolive here is we have a section which right now only contains the Syngen paper on reproducible papers here. And what this is basically a notebook for each of the figures in the Syngen paper which you can reproduce directly in the browser. I think this is a way forward if more papers would start to adopt this, or at least provide code which actually can directly reproduce the figures. It's not possible for all research, but for a lot of different things it might be possible.
Great. So any other questions out there? There's a lot of materials. Again, the webinar will be online, and I'll hopefully get also a copy from you as well of the presentations. And of course, Seismo Live is a great resource for everybody to explore as well as all the websites and links for the different software packages are all very well documented, thanks to the effort of the team here.
Yeah, thanks for hosting us, and also thanks for CIG for all the work you put into, I guess, the open source community over the last years.
Yes, well, we appreciate the efforts of everybody who contributes, and especially those who, I know you guys spend a lot of time helping people online as well.
Okay.
Great.
Okay.
Well, thanks again. And our next webinar will be at our usual time and date. It'll be the second Thursday. That is Thursday, May the 10th at 2 p.m. And we will be talking about the new developments in the soon-to-be-released Aspect 2.0. And that will be presented by the Aspect team of Renee Gassmiller, Julianne Danberg, and John Nalabaugh. So see you guys then. Bye.
Bye.
Bye-bye.